Hello, everyone, and welcome to our third Tech Talk. We wanted this to be more or less reoccurring, which it is, but with not the set intervals. It is all up to you. The last one did not take place because there was not sufficient interest, but I see that that has drastically changed, and I'm very glad to see that. So, without further ado, let's jump into our webinar. I'm going to start sharing my screen and presenting the topic that I wanted to cover today. So, in just a second. Yeah. So again, welcome to Tech Talk number 3. Previously, in Tech Talk number 2, we covered sizing and oversizing of battery banks. There we spoke about charge and discharge limits as they were set by the manufacturers. We spoke about minimum battery size in the context of inverters. We said that the batteries must be able to withstand the stress that the inverters are going to impose on them. And we also spoke about battery degradation and what role that has to play with correct battery sizing. Mostly we were covering the fact that you might have, let's say, I don't know, 100 kilowatt hours of capacity now, and you might need 100 kilowatt hours of capacity. But after degradation, when you don't have those 100 kilowatt hours left in your batteries, what do you do? So you need to prepare in advance, and that's why the oversizing is needed. Today, at least to me, we're going to be covering a more interesting subject. We're going to be talking about common types of ESS and methods of interconnecting them. And obviously, the webinar will be conducted by myself, Avtandil Giorgadze, you can call me Gio, and I am a solutions engineer here at Fortress Power. I focus on residential systems and on supporting the customers up until the point of commissioning or unboxing the equipment in the field. So let's continue. And let's talk about the key factors that we need, or key circumstances and key requirements. So first and foremost, we need to understand that we are not allowed to output, just a moment, I'm so sorry. We are not allowed to apply any voltage to the grid or any parts of the grid, simply put, to the meter when the grid outage occurs. So even if you're doing backup, you're not allowed to deliver any voltage to the meter or anything upstream of the meter. This is very important requirement. This has to do with safety, and the fact that you comply with this requirement is proven by various UL certifications. So for you to be able to visualize that, this is the typical layout. You have main electrical service panel, you have your meter, you have your utility transformer. So everything downstream of the meter is your property. That is what you are powering. So at no point, utility transformer or meter must be energized by your energy storage system or energy generation system, your generator, PV, batteries. Nothing is allowed to apply voltage at the meter. And one could ask, oh, why we cannot do that? Because sometimes grid outages are not accidental because of bad weather or something like that, or because the I don't know, power lines were damaged, but they're planned. They're planned, and linemen are actually going there and performing work. By you energizing your meter, you are energizing the grid. So you're introducing to voltage in the circumstances in which the lineman would expect there to be no voltage whatsoever. So not to create any danger to them, not to harm them, or cause serious safety hazard. That's why this requirement is so important, and that's why you're not allowed to have any voltage applied to the meter during a grid outage, to the meter or anything upstream of the meter. But mainly when working with residential systems or residential products, everything happens downstream of the meter. I've never seen residential product being used upstream of the meter. That is not a thing. So with this important requirement in mind, let's do a quick recap of what we would consider the components to be for a common energy storage system. Well, since this is an energy storage system and we said that it's common, um, we must have battery in place, right? Some would say, well, I mean, hydroelectric plant is an energy storage system too, but it doesn't have battery. It has a body of water behind the dam. Well, you're absolutely correct. That is the case, but context here is residential systems. And um, when we say common, yes, there are other options too, but common is battery based on some kind of chemistry. Uncommon would be something like a flywheel, for example. So that's why I say battery is the common thing that we would expect to be in place when talking about common energy storage system. Then we would expect to see an inverter because, as we know, AC signal really is not inherent to any chemical storage or chemical power generation system. Your PV arrays are based on chemistry, and they output DC electricity. Your batteries are based on chemistry; they output DC electricity. The only thing that I could think that outputs AC electricity naturally is if you have a rotor and a stator and you have rotating magnetic field. That's when really the AC occurs naturally. In all other cases, when we're talking about some kind of chemistry based energy generation or energy storage, we're talking about DC. So inverter is needed to invert that DC to AC electricity so that you can power your appliances, which happen to be AC. The circuits in our homes, in our offices, those are AC, and also grid is AC. So this allows you to export power to the grid if there is such desire or need to do so. Also, inverters, a lot of times, especially modern inverters, have this function in them that they allow you to not only export power to the grid, but also import power from the grid or sometimes from some other AC source, such as a generator, and invert that to DC to charge the battery. So it has a bidirectional function. One function is to take battery DC, turn it into AC, and send it to the grid, or send it to the circuits in your home. And the other function would be to take the AC from the generator or from the grid, turn that into DC to charge your batteries. If, for example, PV is not available or something of that sort. And also, just like we said before, because we have this requirement, um, we must have anti-islanding protection so that an energy storage system or whatever power source you have cannot apply any voltage to the grid. So these things, at least, we would expect to see when we are focusing on common energy storage system. So that is energy storage system, but the reality nowadays is that energy storage systems are used in tandem with something else. We're going to get to that later. But before we do so, I wanted to outline a couple of different configurations of the components that we have mentioned here. So in some cases, although I have battery, inverter, and anti-islanding protection as three separate things here, sometimes these things can be in one enclosure, really creating one unit. For example, you could have battery and inverter in one enclosure, qualifying as a single energy storage unit. So you don't have a standalone inverter and standalone battery, but you have the two merged together in one enclosure, forming one unit. Sometimes you have anti-islanding protection and inverter also merged in one unit. Um, Example of that would be actually our inverters. Our NV inverters have anti-islanding protection built in them, so you don't have a separate unit anti-islanding. It's within the inverter, but the battery is standalone. So you need to have battery unit, inverter unit, and connect the two together when you're working with our equipment, for example. But other manufacturers choose to have one energy storage unit in which they have the inverter and the battery cells, and that's exactly what it is. It's just one unit. Also, um, the thing to remember about anti-islanding protection device, it doesn't have to be of certain shape or form or whatever it is. Um, Sometimes it can be like a small box. Sometimes it can be embedded in the equipment so much so that unless you disassemble the equipment, you don't see it. And in some cases, it's very much visible. Specifically, what I have in mind is when you're using a meter collar, for example. Yeah, I mean, it takes the face of the meter and pushes it out because it also, among other things, acts as a spacer. Really, when we're talking about anti-islanding device or anti-islanding protection, I want you to think about it as a functionality and not a separate device as such. And mostly at this level of abstraction at which we are during this webinar, I would like you to think of everything as a function rather than one physical device that you would have in mind. And that applies to me too. When talking about this stuff, I'm going to forget about the fact that I work for Fortress Power and we have batteries and inverters detached from one another and the anti-islanding protection built into that. No, I'm not going to have NV inverters and eForce batteries in mind when I'm talking about it, all the way up until the end. Then we're going to focus for a moment or two about how we do things. But meanwhile, let's continue with the webinar. So, as I said before, in conjunction with energy storage systems, we very frequently see solar arrays, and frequently, but not as frequently, we also see generators being used. So, really, solar arrays is the biggest thing that is external to the energy storage system and works with the with the energy storage system when the grid is unavailable. Generators, yes, they're common, but not that common. They're quite common in backup specific applications or perhaps even in the applications that could be called off-grid, where they don't have grid at all, or they want to rely on the grid as a backup. But yeah, nonetheless, these two are quite common, and there are a couple of words I want to say about them as well. So, solar array. When we talk about solar array really is just a combination of PV modules. But that has nothing to do with their input and output because they may be used in different configurations. And when used in different configurations, that leads us to different results and different requirements and so forth. So solar arrays, as I said, a few words about chemical power production or chemistry-based power production or storage, as I said there, those tend to be DC electricities that we get out of those. So PV modules are not an exception. PV modules, when there's enough irradiance and they generate electricity, they generate DC electricity. But as we said before, we need AC electricity to power our appliances or to send power to the grid. So some kind of inverter must be there for the solar array to be useful for the user. So there are two ways for standalone, and not only standalone, but in general, there are two ways to turn that DC electricity and turn into AC electricity. One way is AC coupled PV array, in which you utilize microinverters. So behind each module, you install a microinverter. So each module has its own. So right at the modular level, the output of the PV, the DC output, is inverted into AC output. You have multiple of these microinverters. You group them in the strings, and then combined output of these strings is sent to your grid, to your appliances, to your inverter, whatever it is. Now, the other school of thought or the other method of converting DC electricity from the modules to AC is to use string inverters. So, well, as I said, with microinverters, you create a string of microinverters that have modules connected to them. But when we're talking about DC coupled PV strings, what we mean is you have the modules connected in series with one another, and you have a DC string, which is very high voltage DC string. And then that string goes to the string inverter that takes that high voltage DC signal and turns it into a 240 volt AC signal, or 280 if you're using commercial. But most of the time in residential, we don't see 208, we see 240. So really two different approaches, very similar, and as a result you have AC output that you can use. But microinverters, you have strings of microinverters, small AC power sources, and in DC you have long string of DC power source with PV modules in it, and then string inverter delivers the AC on the output. In some cases, the string inverter functionally is incorporated in the battery inverter. So what do I mean by that? You have the MPPTs in your battery inverter that if you want to charge the batteries, there's DC to DC controller, and you can adjust the voltage accordingly for you to safely charge the battery. But also you have the inverter, the battery inverter, turning that DC from those strings to AC that you can use then for your backup or for export to the grid. So essentially, think of it like the battery inverter having the string inverter built in, right? Then another important point when we're talking about generators and generator interconnection. If you have a generator with no energy storage system, you just have your electrical panel, you have your generator, and you have your grid. Generators have automatic transfer switches. So if you were to go and do a retrofit with energy storage system, and you know that there is already a generator, you right away expect that generator to have an automatic transfer switch. What automatic transfer switch does is during a grid outage, it changes the arm position. And with the arm position change, the power source for your loads becomes the generator, whereas the grid ports are isolated from the generator and the loads. And then when the grid comes back on, the arm returns into its normal position, right? So this is also a way of doing anti-islanding, and it's very, very common with generators. So with these aspects covered, we need to recall the typical layout and say that there are two ways to tap into the existing layout or normal layout. So typical layout, we said that there's utility transformer, then there is your meter, and then there is your main electrical panel. And the electrical panel really is your load panel. That's where all the loads live. So if you put your energy storage system somewhere in between the main electrical panel and the meter with an appropriate overcurrent protection, of course, throughout this webinar, assume that there is overcurrent protection if you do line side tap or load side tap. But if you connect somewhere between the meter and the main electrical panel, we would call that a line side tap, because we're looking at it from the point of view of the electrical panel. So line is here, so it's line side tap. But there's another way of doing it. You can connect the energy storage system directly to the main electrical panel, and that is what we would call the load side tap. So if we are somewhere here, right? This is the load side, this is the line side. We connected our ESS here on this side. This is the load side tap. We connected something on this side. This is the line side. So with that, I think we're ready to explore different configurations and different methods of interconnecting. What are the limitations? What are the pros, cons? And then at the end, see how Fortress Power does it. So this is the most basic, at least if you ask me, way of interconnecting your energy storage system. This is common with certain manufacturers, so to speak. I don't want to I don't want to advertise them in this webinar, but I think some of you that have experience in the field know who I'm talking about. So you have your energy storage system, which is battery and inverter as one unit combined, and you have anti-islanding device, specifically a meter collar, connected to the meter. And you have your main electrical panel. So what this allows you to do is when there is an outage, this allows you to separate from the grid via anti-islanding device that sits right at the meter, and then your energy storage system to provide power to the loads. And that's why it says right here, for the backup to be possible, the SS must be AC forming. So this should actually form signal for your loads for them to be backed up. Whereas, for example, when I was talking about the micro inverters, when I was talking about the string inverters, AC coupled PV inverters in general, they don't form a signal. They just follow the existing frequency of the grid. So when the grid goes off, they go off. When the grid is available, you will not see different different frequencies or different signal type or anything like that. No, you would see that the AC coupled PV is following the existing grid signal. So in this case, is the backup possible? Yes, absolutely. And anti-islanding device makes this all safe for the lineman or whoever is working upstream of the meter. And meanwhile, we enjoy our energy storage system doing its thing. But we don't want just energy storage system. We also want PV most of the time. So in some cases, with certain manufacturers, you can connect the DC coupled PV to the energy storage system or AC coupled PV to the energy storage system directly. In some cases, you cannot connect the energy store. You cannot connect the AC coupled PV directly to the energy storage system. You need to connect it somewhere upstream of it for it to be able to utilize it. But still, that AC coupled PV is between the anti-islanding and the energy storage. So once the energy storage system starts forming the signal, the AC coupled PV will be following that signal. So not only the benefit of having energy storage system in such cases, not only that you will have battery backup, but also you're going to keep your AC coupled PV alive. So you will have backup coming from two things: your energy storage system with the energy that it has stored, and the AC coupled PV, which will be constantly generating power as long as there's sufficient amount of light. That's why it says over here, for the backup to be possible and for the AC coupled PV to be enabled during a grid outage, the SS must be AC forming. Next, what if we want multiple devices? What if we want to have also the generator interconnected and we want to have AC coupled PV? Well, in this case, some manufacturers introduce something that you would call microgrid interconnection device. And in such cases, microgrid interconnection device can have anti-islanding device built in or anti-islanding device installed as a meter collar or somewhere upstream of the microgrid interconnection device. First, let's cover the case when the anti-islanding device is built in. So you have your main electrical panel, and it is supported by microgrid interconnection device, if you really think about it. But microgrid interconnection device takes power out of these three components: ESS1, ESS2, so two different units, or inverter 1 and inverter 2. You can have inverter which has one AC port for backup and grid connection. So what happens here is that I should have mentioned this probably before too. In all these cases that we have discussed so far, there's one group of AC ports, L1, L2, neutral, perhaps grid, or perhaps ground, and that is the one interconnecting to the rest of the system. So based on the grid availability, those ports either serve as the backup ports. So if the grid is unavailable and you still have voltage, That is your backup port, right? Or when the grid is available, an anti-idling device allows that power to flow to the grid, you have the same ports responsible for exporting power to the grid or importing power from the grid if you need to charge your batteries using the grid. So returning to this, if you have inverter or inverters and the energy storage systems as a standalone unit with a battery and inverter built in, and you have one group of ports responsible for backup and responsible for import and export, then microgrid interconnection device is kind of something that makes a ton of sense. So you have your generator, you have your first inverter or first energy storage system with inverter and battery built in, and you have your AC coupled PV. So everything here outputs AC, right? And all that AC goes to a microgrid interconnection device, which really manages the power flow. So when the grid is available, obviously the power comes from the utility transformer through the meter, flows through this microgrid interconnection device, and then goes to the main electrical panel. That's why we say here that ESS must be the microgrid interconnection device must be able to support enough AC pass-through to the main electrical panel. So everything that the main electrical panel demands, you should be able to pass through the microgrid interconnection device. Otherwise, the conductors will melt, really. So when the grid is available, anti-aligning device is not separating the microgrid interconnection device from the meter. And what you can do when the grid is available is send power from the energy storage system devices or AC coupled PV output to the grid, or supplement the import so that your main electrical panel demands less electricity than it would have otherwise. But when the grid is unavailable, your anti-islanding device will separate the entire local system from the meter and utility transformer. Obviously, batteries will be the first line of defense. They will start outputting power. Inverters will be forming the grid. AC coupled PV will be following that microgrid. That's why it's called microgrid interconnection device. But if it so happens that at some point your PV is not producing enough power, your batteries are depleted, then microgrid interconnection device, since it has the generator connected directly to it, should be able to start the generator, and power from the generator will flow through the microgrid interconnection device to the main electrical panel. Again, nothing will flow to the meter because the MID, or microgrid interconnection device, is ensuring that the anti-islanding device is in such a position that connection to the meter is interrupted. So while you're sending the generator power to your main electrical service or main electrical panel, to your loads, your energy storage system is allowed to take some of that power and charge the batteries. So microgrid interconnection devices are pretty cool. And obviously, when the generator is running, your inverters or energy storage devices, they are not allowed to form any signal or any frequency or any grid. They're only allowed to follow the frequency that the generator provides. Otherwise, one could backfeed into the other, and that will be a disaster. That will be equipment damage. That's why we say here that ESS must be able to enable, disable the generator. Obviously, it should be able to call for the generator when it's needed, and must be able to be AC following and AC forming. So it's following when the grid is available or when the generator is available, but it must be forming when the batteries are to do the backup. So is backup possible here? Yes, absolutely. In some cases, as I said before, the anti-islanding device can be outside of the microgrid interconnection device. That is also fine. Nothing changes here except for the fact that your anti-islanding device does not live in the microgrid interconnection device. the same scenario that we discussed before, but without the AC coupled PV can be considered common. What we see here is everything is the same in terms of what the microgrid interconnection device does, what anti-aliasing device does, what energy storage system does, and what generator does. So everything remains the same. The only difference is that you have DC coupled PV output connecting directly to the energy storage system. You don't have standalone AC coupled PV inverter connecting to the microgrid interconnection device. This actually is my preferred method if it's possible to have DC coupled PV connected to the energy storage system as one device, or to connect the DC coupled PV to the inverter directly. This is my preferred method because this is more of a controlled environment. Plus, it's more efficient charging because it's DC to DC charging. So rather than inverting twice, you are just DC to DC charging, and anything that is DC and has to find its way to the AC, only then inverting takes place. Or if the meter, or if the generator or the grid is available, once only you invert the AC power from the generator or the grid to charge your batteries. And same scenario here, but anti-islanding device not living inside the microgrid interconnection device. Again, different manufacturers take a different route. Now let's talk about partial home backup. So far, we were always covering the main electrical panel, right? Now we have main electrical panel and the critical load panel. So meter collar here will not be relevant anymore, right? Because if the meter collar is in place, everything downstream of the meter can be energized. So your microgrid interconnection device, if the meter collar was to be here, would energize the main electrical panel and the critical panel. Whereas we want only the critical load panel to be energized, right? And because of that, the anti-islanding device must be somewhere downstream of the main electrical panel. And the most likely place for it is inside the microgrid interconnection device, if you have one. So you have, again, your AC coupled PV, your generator, your batteries and inverters. But here, everything upstream of the microgrid interconnection device is offline and separated from the rest of the system, which in your case happens to be main electrical panel as well. So only critical load panel is allowed to take power. Same scenario with DC coupled PV, nothing changes in those regards. And now we move to another but different common energy storage system configuration. So here you have inverter. You don't have maybe inverter, maybe one unit with the battery and inverter built in. Now we're talking about only the inverter, which has the battery attached to it. So in all of these cases, when you see at least two AC ports are used, this type of thing, and only inverter here, assume that the battery is connected to it. It's just I didn't want to overcomplicate this diagram, or the diagrams following this one. That's why I don't have separate box for the battery. But assume that the inverter is here and the battery is connected to it. So we still have utility transformer, we have your meter, and then instead of microgrid interconnection device, we have an inverter, which, if you think about it, incorporates microgrid interconnection device functionality in itself, because you still have generator connected to it, you still have DC coupled PV or AC coupled PV. I'm going to spoil you a little bit, so spoiler alert here, but we can do both of those at the same time, precisely because we use this type of approach with our inverters. When you have the inverter kind of having the inverter functionality and microgrid interconnection device functionality, and it can support whole home backup. So here, the inverter, first of all, must be able to facilitate the pass-through from your meter to your electrical service panel. So whatever main electrical panel can possibly demand from the grid, the inverter must be able to pass through that power. Also, you have the generator connected to this inverter, which implies right away that the inverter must be able to turn on the generator and when the generator is running, become AC following rather than AC forming. You also have AC coupled PV input capability here, which also implies that obviously you have batteries, you have AC coupled PV. This means that you can be grid forming. So instead of multiple different devices, you have inverter doing it all. And it also gives you more flexibility when it comes to critical load panel, because right here we have at least 2 AC ports are used on the inverter, at least 2 being one for backup and one for export and import. Why at least 2? Because generator output, AC coupled output, those would require additional ports. But you will have at least 2, one for grid side, one for load side, so to speak. So anti-islanding device built in means that the anti-islanding device will not allow the connection from the grid port to go to the load port. So it will interrupt that pass-through that we were talking about before. The other method of interconnecting this, especially for people that are worried about, oh, what if my inverter doesn't work? What do I do then? I cannot even use the generator because if the inverter is not working, what's going to turn on the generator? For those people, there's this approach that you have the inverter, again, with all the functionality as before, except for direct generator connection. You have a separate standalone generator ATS, which you would have normally without the energy storage system if you were to only have grid and the generator as power sources. And where the grid normally would go, so ATSs usually have normal, standby, and load. Normal is your grid when you have just grid and the generator. Standby is your generator, and load is load. Doesn't matter how, whether it's in this configuration or generator plus grid only configuration. Here, what changes is that the normal side of the generator ADS is the load side of the inverter. So if the inverter is facilitating pass-through, if the inverter is providing power because there is a outage and the batteries and the PV are supporting the loads, your generator automatic transfer switch will just facilitate pass-through from the inverter power to your generator output. But if your batteries cannot provide any power because they're depleted, because there is no sun, your PV strings cannot do any power production, then the generator will see that the frequency and the voltage are gone on the load side of the inverter. So from the point of view of the generator automatic transfer switch, that is a grid outage. So it will do what it would normally do and will change the position of its arms and go from normal to standby as a power source, standby being the generator. So now the generator is allowed to provide power to the main electrical panel, but in this case, what you lose, yes, you have redundancy, but what you lose is you lose the ability to charge your batteries using the generator power. And then when the, let's say, generator was running, grid is still not available, and all of a sudden the grid power came back, right? Then the generator ATS will change the position and will rely on the grid to deliver power to the loads, and the generator will be turned off. Or if the PV started charging the batteries, and because the batteries are sufficiently charged, the inverter came online, then the generator again will be turned off, and the frequency and voltage will do that on the inverter load side, and you would be able to return to that mode when the generator is doing nothing. The ATS is just facilitating the pass-through, and main electrical panel uses the output from the inverter. Same situation here with critical load panel. It's just, it so happens that main electrical panel, in addition with the meter, is upstream of the inverter. Everything else remains the same. And again, here you don't have battery charging capability. And one more approach, when you have two AC ports, one for backup and one for import and export, you can say no to the backup, right? And just have the batteries and the inverters doing arbitrage or export self-consumption, but no backup. So in that case, nothing is connected to the load ports, right? But the battery is connected to the inverter. The inverter is connected to the main electrical panel. You have your DC coupled PV or AC coupled PV also going to the inverter. And this would mean that you have no backup, but you can send the power from your batteries or from your PV to your loads and or to the grid. This sometimes makes a lot of sense, because sometimes people just want the batteries to avoid sending power to the grid as much as possible, because they're not well compensated for their, not well compensated, but they pay more for import of the power than export of the power. And they want to get away with small battery bank and so forth. They don't care about backup. In those scenarios, this is more budget friendly and less complicated installation. And again, this is possible because anti-islanding device is built in. So if you were to have single unit with inverter and battery, but no islanding device, that would not be a safe installation, because what would ensure that the battery and the inverter are not outputting anything to the meter? You need a meter collar somewhere. Here, the meter collar is inside the inverter. So yeah, those are the things I want to cover. And before I show you how we do it, I just want to emphasize one thing. In majority of cases, the line side tap allows you to have more power from your energy storage system than the load side tap. Because think about it. If it's the load side tap, you have one source as grid, the other source as the ESS. And those two can generate together way more current flow than what the electrical panel bus bars can withstand. And you cannot change those bus bars, because that would require you changing the key, the entire thing. Whereas when you're doing the line side tap, it's easier to swap the cable. And if it's going to the load, it's one set of cables. If it's going to the grid, it's the other set of cables. Whereas here, if you're doing load side tap, one set of cables and set of bus bars facilitate all the current flow. And the bus bar being the bottleneck, line side tap would be preferred if you want a bigger installation. I'm not going to go into the details of NEC code. What are the percentages, limitations? I'm just telling you, maybe at some other time I'm going to do a separate webinar on that. But if you want sizable energy storage system, you'll probably have to do a line side tap rather than a load side tap, because on the load side tap you are quite limited. Actually, that would be a good topic for the next tech talk. Maybe that's what I'm going to focus on next. But meanwhile, let's take a look at how Fortress Power does it. And you will notice here all of these major diagrams, which they come from the manual directly. They show light side tap, and there's a reason for that, because we can do 200 amp pass through, and we can do sizable off-grid output of 12 kilowatts. So you have your main breaker or some kind of overcurrent protection, such as grid disconnect, which is fused. So if you try to pull more than 200 amps, it's going to pop the fuses inside. Not both of them are required, really, as long as you have qualifying overcurrent protection device, which could be very well your fuse disconnect. This could be an optional item, I guess, but with only fuse disconnect, you could get away with such installation. You see we have whole home backup here. So normally the power comes from the grid, travels from the CTs. This is our devices. They allow us to measure the power flow to and from the grid. So passes through the CTs and goes to the manual transfer switch. We're going to talk about that later, but for now, forget that there's a manual transfer switch. So goes through the manual transfer switch to the grid ports of the inverters, and then there is a pass-through from grid ports to the load ports, and that travels to your main electrical panel. So this is the scenario when the grid is available. Power comes from the grid, travels through the inverter, comes out of the inverter load ports, and goes to the main electrical panel. And your batteries are there to reduce the import. Your PV is there to reduce the import. Perhaps if you have enough power, even export something to the grid. But the moment when the grid outage occurs, your connection right here is interrupted. So you're not connected to the grid anymore. You will see no voltage here when the equipment detects the grid outage. Then your batteries, your PV, your generator, if it has to come on, will send the power through the load ports to the main electrical panel, but nothing to the grid ports, because the anti-islanding device, which was facilitating the pass-through, interrupted the connection. So nothing can travel beyond that anti-islanding device. And again, we're keeping the things safe here. You will also notice that we have DC coupled PV ports on our inverters. That's because we essentially have those string inverters built. Hi, apologies. This is Gio again. I'm so sorry. Something happened to my computer, so I'm using my colleague Anthony's computer. I guess it just shut down because the battery was depleted. Very, very ironic that I'm talking about the batteries and the batteries dying on my computer. But it is what it is. I only had two more slides left. Obviously, as I said, those diagrams come from the manual itself. I was just going to show you the critical load panel, how it ties in with our inverters, and how you have multiple inverters connected together and working with our how we have multiple of our inverters working with the loads and the generator and so forth. But it's very straightforward. Really, the concept remains the same. It's just you use the combiners. So yeah, for today, that's all we have, because we have this emergency, so to speak, that my computer is not available. I would ask all of you to send in your questions via email if you have any. Well, hopefully see you next time. I promise I'm going to connect my computer to the charger before starting the webinar. And yeah, I wish you all the best. Best of luck in your future projects. Don't forget to secure your energy with Fortis Power. And yeah, Tech Talk 4, probably LightSat tap, load side tap, what are the advantages, and so forth. See you next time. Thank you very much. Bye.